In this lecture, we want to take a look at inheritance and interfaces. What is inheritance? Well, as you notice, all of the objects or classes listed here in this chart are all people. That is, a student is a person, an undergraduate is a person, a lecturer is a person. All of the entries here in this chart are all people. And so we could have a superclass called person and put in class person those things, properties and methods that are common to all people. For instance, every person has a name, an address, a phone number, a birth date. And if we restrict this to SDSU personnel, then all of these people have red IDs. Because all of these people have in common a large set of properties, we can put these properties in class person and then inherit from class person for more specific types of people. If we do this, then we can create something like class faculty that inherits from person, and the syntax for that is public class faculty extends person. And if we do this, then the faculty class inherits all of the properties and all of the methods, that is, all the variables and methods that are in class person. The benefit for doing this is we no longer have to include name, address, city, state, zip, red ID, and so on in faculty class. Without this mechanism, we would have repeating code. That is, we would have to have string name in class person and string name in class faculty and string name in class professor. And this is not desirable. Rather, we can, in the more general class, put the properties and methods that are common to it there and then inherit them. So this gives us code reuse, and it also simplifies the code. So at each level, as we descend the inheritance chain, we have more specific objects. Professor is a specific instance of faculty. Faculty is a specific instance of person. So each class, as we go lower down the chain, gets larger. Though they might actually appear to be smaller, they may have less code in them because they inherit everything from the parent. So I'm sure that this is in some ways familiar to all of you. You have seen this before in preceding courses. A lot of times inheritance charts are given with things such as animals. You have class animal, and from that inherits class dog or class cat. But these seem really impractical, and in fact they are. It isn't too often that we have this type of inheritance chain. There are, of course, situations where it is relevant and important. A good example of that is graphical user interface code. There we have many graphical user objects that are placed on the screen that have similar properties and methods, and they inherit from one another, so you can have a very deep chain where what you have is a specialization of the upper level class. But what's really important in CS310 and what we're primarily concerned with here is polymorphism. This is the real power of object-oriented programming. The big idea is this. Suppose I have some kind of container class and I want to store things in it. Can I create a container class that will hold persons, faculty, professor? Can I create a container class that would hold things like inventory items, instances of all these people, perhaps repair jobs, or even scientific data? Moreover, can I have a single container class that would hold all of these different types of things? With the procedural type of programming that we had before object-oriented programming, this simply wasn't possible. If you needed, for instance, a stack to hold integers, and then you needed to use floating point numbers in your stack or strings, then you would have to create separate objects for each of those things. With polymorphism, the answer to the big question is yes, we can create one container class that will hold anything. We can have a container that will hold any type of object, including objects we haven't even written yet. This is a main topic of the course and one we will consider in some detail. But at this point in the game, we want to understand inheritance, so we want to take a look at the mechanisms of how it actually works. So here's a simple example base class. And again, if we restrict this discussion to SDSU people in the chart we just saw, there are certain properties that all SDSU people have, whether they're students, employees such as staff, groundskeepers, janitors, or professors. Everybody has a red ID. Everybody has a name, an address, a city, state, zip. Everybody has a birth date. Therefore, we can locate these properties in the base class and then inherit them when we extend this base class to other subclasses. So the get red ID, set red ID, get title, these will be inherited down the chain. So here's an example of a derived class. Faculty is inherited from person. So the syntax, of course, public class faculty extends person, and the keyword extends means that it inherits from person. Thus, faculty automatically has name, address, city, state, zip, red ID. Every field, every variable that's in class person that isn't private is inherited, and so we don't need to repeat that information. What we need in class faculty is only what is different. So we have position, we have tenure track, which is a Boolean. That is, faculty can be roughly divided into tenured track or tenured faculty versus non-tenure track. That would be lecturers, instructors, and so on. So these are specific to faculty but not applicable to person. But this class inherits everything in person. So here we have a class that inherits from faculty, which of course inherited from person. Public class professor extends faculty. Thus, professor has everything that's in faculty and everything that's in person. And what we include here inside class professor explicitly are those things that are different. So we have a number of properties and methods here that are different from class person. For instance, we wouldn't want to put set or get salary inside class person. We don't pay everyone. For instance, we don't pay students. So having a pay method there doesn't really make any sense. Some assignment statements to look at here. Person P1 equals new person. Well, we can do this, but it's not really useful. We generally want to instantiate more specific people, more specific instances of person. So I can say person P2 equals new faculty, person P3 equals new professor. Now we can do this because person is a superclass. Superclass or base classes can point to derived classes. So the left-hand side here is important. The pointer, the reference on the left-hand side, it can point to any of its descendants. So a person reference can point to a person, a faculty, a professor, a student, any of the people in that inheritance chain. We'll talk about why we want to do this in just a moment, but what becomes possible here? We have three print statements. Get title. Well, this works for all three. That is, all of these statements are perfectly valid. In the case that it's a person, we get Mr., Mrs. In the case that it's a faculty, we get faculty member. In the case it's a professor, we get professor. So the idea here is polymorphism. That is, P1, P2, and P3 are all variables of type person. But at runtime, the appropriate method is found and used depending on the actual type on the right-hand side. Then moving down, notice that we have P1, P2, and P3 .pay. This code doesn't compile. Now notice that in the case of P3, it's actually a professor, but there is a pay method in class professor, but it still doesn't compile. It doesn't compile because P3 is a variable of type person, not a variable of type professor. The pay method does not exist in class person, so it will not even compile, let alone run. We can get around this by casting P3 to a new variable P4. So P4 is of type professor, and now we can call P4.pay. Yes, this will work. So the main idea here that I want to call your attention to is that of polymorphism. And it turns out that this is actually the foundation for much of object-oriented programming and the foundation for generic programming that becomes really important in CS 3.10. So there's one rule I'd like you to remember. Parents can point to their children, but children can't point at their parents. That is, on the left-hand side, person can point to any of its descendants. Person is the parent class. It can point to or refer to any instance of its children. So faculty is a child class. Professor is a child class of person. Therefore, person can point to, can refer to an instance of faculty or professor. But the reverse is not possible. We cannot say professor P4 equals new person. This will never work. The reason it won't work is professor is a larger class. It has more things. So if we were to say professor P4 equal new person, what would happen if we called P4.pay? There is a pay method in professor, but there isn't one in class person. So this would never work. So the rule to remember is that parents can refer to or point to their children. Children cannot point to their parents. It helps to remember that in real life, parents can point at their children if they want to, but children pointing at their parents is considered rude. So that's kind of a helpful way to remember it. When I say parents point to their children, I mean parent on the left-hand side references an instance of, a descendant of that class on the right-hand side. So we can say person P equal new professor, but if we do this, it means that only methods that exist in class person can be invoked on P, no matter what the actual type is. We can't possibly do P.pay, even though there is a pay method in class professor, because there isn't one in class person. We can, however, do the following. Professor prof equals new professor, prof.getRedID. There is no getRedID class specifically in class professor. There is because it's inherited from class person. So the JVM will go up the inheritance chain looking for a matching method, but never down. Prof is a variable type professor. There is no getRedID in professor, but there is in fact one in class person. So another rule, the first one was parents can point at their children, but children can never point at their parents. The next important rule to remember is that children inherit from their parents. At least they hope they do, but parents do not inherit from their children. Therefore, the inheritance chain goes only one way. The JVM will look up the chain but never down. Thus, person P.pay won't work because that would require the JVM to go down the inheritance chain to find a matching method, but it will never do that. There are several different types of inheritance, reasons why you might use inheritance. One is specialization. That is, a derived class can be a more specific type than the base class. So this is the example of professor being a more specific type than faculty, which is a more specific type than person. All of the methods and the variables, which we sometimes refer to as properties, are inherited from this base class unmodified, and new ones specific to the derived type are added. So the professor class is more specialized than faculty, which is more specialized than person. The second type of inheritance is specification. This is used to guarantee that derived classes have a specific set of methods with specific signatures, and this is done to ensure consistency. As an example, a container base class might use the signature public void clear. So we might have this in a data structure, superclass that has the signature public void clear. And having this method is used to ensure that all derived classes have precisely that signature to return the container to an empty state. Thus, it enforces consistency. All child classes will need to have a clear method or use the parent method. The third type of inheritance is wrapping. That is, the derived class changes the behavior of some methods in the base class, but the essential behavior of the base class isn't changed. So an example of that is the class map in the Java API. Map is a type of dictionary, and it stores data based on keys. So an example of this might be people at SDSU. The key would be the red ID, and then the value, the rest of it, the rest of the record for that person. So maps handle duplicate entries in different ways. That is, if we're talking about SDSU people, it's obvious that we can't have two people with exactly the same red ID. This would never work. They might have the same name, but they can't possibly have the same red ID. Each person must have a unique one. And so the way this gets handled can vary. In the Java API class map, it works by overwriting existing ones. Thus, if you try to insert a new record and it's a duplicate, it will overwrite the one that's in the map now with the new record. This may not be the behavior you want. You might want, for instance, to have a check first, that the insert method checks to see if that red ID exists, and if it does, then it could either return false or throw an exception to prevent a duplicate from being inserted. So what you could do then is extend the map class and override the insert method to get the behavior that you want. So wrappers are fairly common. You take an existing data structure and you do not have to write it from scratch. You do not have to reinvent the wheel, but you can modify by overriding the methods in it to get exactly the behavior that you want. There are other types of inheritance, but these are the main ones we want to look at in the data structures course. Another important idea here is the interface. Interfaces are primarily used for abstract data types. So I want to talk about abstract data types for a moment. This is an important concept. An abstract data type, or ADT, describes behavior but never the implementation. For example, if we need a stack, we can create that stack by using an array, or we could use a linked list if we wanted to. Both ways are valid, and the behavior would be just the same. The push and the pop would behave in the same way. And so the big idea here is that stack can be an ADT, an interface, an abstract data type that specifies the behavior but not how it's implemented. Removing the implementation from the equation simplifies programming. An application programmer just needs a stack, but the application programmer doesn't really care whether it's done with an array or done with a linked list. So we want to make this distinction. It's all about behavior versus implementation. So as an example, ADTs. The following are abstract data types, or ADTs. A list, a stack, a queue, a map, a dictionary. And these are abstract data types because what we specify is the behavior, but not how it's implemented. Data structure, however, these are the actual implementations. And so a stack is not a data structure. A stack is an abstract data type. Data structures are things like linked lists, arrays, binary search trees, heaps, and so on. We use interfaces in Java primarily, as I said, to specify behavior. They behave very much like an abstract class. One of the issues with Java is it does not support multiple inheritance, but there are times when you really need to inherit from more than one class. This is not done in Java for performance reasons. C++ supports multiple inheritance, and there are many experts in the field that believe that this is a mistake. It creates very complex compilers, and handling the type of multiple inheritance issues becomes an issue for performance. So Java got rid of it. You can only inherit from one class. In the case that you need more than one class, then we have the interface. So in many ways it behaves like an abstract parent class, but there is no code. The methods in an interface are signatures only. That is, rather than an open bracket in a body of code after the method signature, you have a simple semicolon. Variables can be declared in an interface, but they must be assigned a value, and they are by default final. A class may implement multiple interfaces but extend only one class. A class that implements an interface must implement all of the methods in that interface. This is an important point here. In this class, we will ask you to implement an interface. And what you will find as you do this is you cannot follow the method many students prefer, which is add one method at a time. Rather, you must have all of the methods in the interface or your class will not compile. Therefore, it's a good idea to add the signatures of all of those classes and then use what we call stubs. That is, if it's a void method, then open bracket, close bracket. If it's a Boolean, then just put return false. Put in some dummy value so that you can get it to compile. But you will need to include all of the methods in the interface in order to get the implementation you're creating to compile. The main reason to use interfaces is specification and polymorphism. That is, we want to codify behavior. For instance, if we're going to have a stack, we need the methods push and pop. We don't want insert or remove. We want push, pop, and every implementation of that stack should have exactly those names and nothing else. This enforces consistency. Then we have the polymorphic behavior that allows us to use this consistent interface to interact with any implementation of that interface. Alright, so the alternative here and what's wrong with it, why do interfaces make sense and why are they important? So back to class person, we could have made this class abstract, and in fact it may make sense to do so, making the class person abstract because nobody is just a person. They are an instance of a person. That is, everyone associated with SDSU is either a student or a faculty member or staff, but just a person. No one is a person and nothing else. They have some other role. So we could make this abstract, and you can make the case for that. Then, with abstract classes, you can implement methods such as getRedID. You can put the implementation there, and it is inherited in the normal sense. But we could also include something like public abstract void pay. And I have the note here, does this really make any sense? No, it doesn't. We're not paying everyone. We're only paying employees, whether they're faculty or staff. We don't pay students. Well, the problem is if you want to have person.pay, you have to have a pay method in class person. The example we talked about previously, if we have Professor P and we declare him as a person, person P equals new professor, we cannot say p.pay because the pay method does not exist in class person. We can get around this problem by including one. We could put public abstract void pay inside of class person. Again, this is a really bad idea for many reasons. We want pay where it belongs. Moreover, as we descend the inheritance chain and each class gets more specific, you add things. Students have things like GPAs. Well, if we want to have on the left-hand side a person and on the right-hand side a student, but we want to be able to get their GPA, then we need also to add public abstract get GPA. In other words, if we take this tack, we're going to end up loading up class person with a bunch of abstract methods that don't belong there. This makes no sense. And so the example I've given here, we have public class student extends person, and then we've got a pay method in it. Well, that makes no sense either, but if we have abstract void pay in class person, we have to have public void pay in class student if it inherits from person. All abstract methods must be implemented in the implementing classes. So this makes no sense. Nor does it make any sense to put GPA inside class faculty. This makes no sense. There is a better solution. Even if we could do this, how would you implement it? So here in the case of student, you can throw an exception in the case that someone accidentally calls this method, which makes no sense and it shouldn't be there in the first place. There is a better way. We can use interfaces to do this. So here we have a simple interface, and there are quite a few of these simple interfaces in the Java language. This one has exactly one method. There are other interfaces that are part of Java that you will use extensively that also contain no more than one method. Here we have public interface payable, public float pay. All right. If we implement this interface, that means we must have a pay method inside the class that implements it. Thus, we can put payable in the classes where it makes sense. So in a sense, what we're doing here is class professor derives from person and also derives from payable. Payable is a slightly different type. It's not an abstract class, rather it's an interface. So we have public float pay, and then the code to do that. It makes perfect sense here, and this allows more flexibility, and it helps to avoid adding inappropriate specificity to higher level classes. That is, this allows us to avoid things like putting GPA in class person or pay in class person. There are differences between abstract classes and interfaces. I pulled this list from www.javapapers.com with a few minor modifications. Always a good idea to cite the source if you're using someone else's stuff. And this seemed like a pretty good list, so I copied it and made some modifications. So the big difference is interfaces really are abstract, but they can never have an implementation. Thus, with an interface, you have only signatures of the methods, but you never have code. An abstract class can have code. So if we made an abstract class person, we could have methods like get and set name, get and set address, and these would be inherited, and they would exist and apply to all descendant classes. But with an interface, you cannot do this. Number 2, variables declared in Java interfaces are final. An abstract class may contain non-final variables. Thus, you can't change a variable that's set in a Java interface. For instance, you might have a variable in interface stack. With some implementations, size makes a difference, or size is important. If it's an array-based stack, then the array must have a maximum size that you cannot exceed. For business reasons, for logic reasons, you may want to limit the size of a stack. Therefore, you could include a variable inside the interface stack, something like public static final int default max size equals 1000. But you could not change that variable at runtime or in any implementing class. But with an abstract class, you can do this. Members of a Java interface are public. You cannot have private methods inside an interface, but a Java abstract class can have the usual public, private, protected access. But everything in a Java interface must be public. The reason is it can't be implemented in the interface, but it must be implemented in the class that uses it. A Java interface is implemented using the keyword implements. An abstract class is extended using the keyword extends. An interface can extend only interfaces. An abstract class can extend another class, and it can implement multiple interfaces. So any Java class can implement multiple interfaces, but only one class, period. Interfaces then are completely abstract and cannot be instantiated. A Java abstract class can't be instantiated either, but it can be if you put a main method in it. So here's a simple interface example, public interface stack. And we have methods push, pop, size, is empty, is full, clear. So if we want to implement this using an array or a linked list, we can do this, but we must include all of the methods in this interface. So this interface is all about behavior and not about implementation. This interface can be implemented using a linked list, using an array. It doesn't matter. The behavior is the same in every case. So here's the simple beginning of how we might implement this. Public class array stack implements stack. I'm missing an S there. It should be implements stack. Then we have our array, and we have size, max size, the constructor, which never appears in an interface, but it does in the implementation, push, pop, and the other methods that aren't shown here. This is an implementation of an interface. Now we can use this interface on the left-hand side as a parent reference. That is, we cannot say stack equals new stack. That won't work. There's no code there. But we can say stack equals new array stack. We can have on the left-hand side of an assignment statement the equal sign. On the left-hand side, we can have an abstract class or an interface. If and only if on the right-hand side we have a concrete implementation of that abstract class or interface. So the reason to do this, could we say array stack equals new array stack? Yes, of course we could. Well, why would we want to use the parent pointer instead? Why would we on the left-hand side put stack instead of array stack? This technique is common and it enforces consistency. It follows the object-oriented framework for developing data types and the data structures that implement them. You could build a project that has many thousands of lines of code in it that uses a stack. And you might have hundreds of lines of codes that refer to your stack. But if you needed to change the implementation of your stack, then you would change only one line of code. Instead of new array stack, you might need to put new linked list stack. But you wouldn't have to change any of the rest of your code. It wouldn't be necessary because you have the behavior of the parent pointer. So you might prefer an array-based stack because it's faster. Array-based structures are faster than linked list-based ones. But you might at some point discover that you need a linked list-based one and it's a better choice. So to make that switch, you change one line of code rather than rewriting the entire class. Finally, I want to call attention to something else, something slightly off topic here. Inheritance versus composition. There are two ways to use existing code in a new class: inheritance and composition. Inheritance, which we've been talking about, should always reflect an is-a relationship. So, for instance, faculty is a person, professor is a person, student is a person. We use composition, however, for has-a relationships. That is, a class has an instance of something else inside of it. So here's a composition example. We could have implement our list stack by using a linked list. So we're still implementing the stack interface, but we're using composition to create the concrete instance. So we have a linked list based stack, and we already have a linked list written, so we can just use it to build our stack. So in the constructor, we make a new linked list. We have our standard methods push, pop, size, and the rest of them, except there's no linked list code inside of this stack, this list stack. There are no nodes, there are no manipulations of lists, only method calls on the existing class. Thus, you can use composition to build new things. Is a linked list a stack? No, it isn't. Can you use a linked list to build a stack? Yes, you can, and this is an example of doing precisely that we are showing you here. So this is a way to include an existing class. Repeating behavior, repeating code can be avoided by either inheritance or composition. Composition should be used for has-a relationships. Inheritance for is-a relationships. Some benefits of using inheritance and interfaces. One is the elimination of redundant code. This is kind of self-explanatory. If we have name, address, city, state, zip, and class person, then we don't need to repeat the variables name, address, city, state, zip in class faculty or class professor. We have software reusability. We're reusing these parent classes. We have increased reliability because we have a smaller code base at the level where we're actually coding. We have consistency because interfaces enforce this. This allows us to have software components and an API library. One of the big benefits of Java is the huge API library that exists. If you stop and think about it, if we have a container class, that is a class that is a type of data structure that can hold information, how could we pre-write these without knowing what's going in them? Can we have a container that will hold anything? And the answer is yes, we can. There are certain complexities of this that we will be discussing in future lectures. One of these, suppose that the container is in order, that the objects stored in the container have to be in sorted order. Well, how do you sort objects when you don't know what they are? You could have geometric shapes, you could have scientific data, you might have inventory items, you might have a collection of students. How do you sort items when you don't know what they are? How do you rank them? We need to be able to compare them. If you want to look up something or search for something in this collection, you have to have a way of comparing it with what you're looking for. So you need a way to compare or rank objects that you know nothing about. This is what inheritance buys you. The exact details of this we will be discussing in detail. But inheritance allows you to write code to sort objects of any type. And this is an extremely powerful technique that you're going to learn how to do in this class. Inheritance provides information hiding. That is, the information goes the place where it needs to be and is not exposed everywhere. And then polymorphism, again, this is the idea of parents pointing to their children. On the left-hand side, you have a parent reference or a parent class, generally an interface. On the right-hand side, you have the concrete instantiation of that interface. You have a parent that refers to or is a reference to a concrete child class. And this is the mechanism that supports generic programming. This is the mechanism that allows us to create containers that will hold any type of object. This concludes the lecture, and we will continue with our discussion of inheritance and interfaces when we talk about generic programming.